It's amazing what today's computers can achieve. They can help us achieve new limits that wouldn't have been possible many years ago. For example, not so long ago, video game characters would look like little pixels, and just a few years later, we can now create lifelike characters that are beyond belief. We have such things such as face scanning technology, computers that can solve millions of equations per second, that can predict weather from satellites orbiting our planet, even computers that can learn on their own. Companies like Apple, Intel, etc. are making chips that are smaller and yet can generate more processing power every year. So how are they able to keep doing this? This phenomenon is known as Moore's Law, which states the number of transistors on an integrated circuit will double every 18 to 24 months. In other words, they can fit more transistors into a small space every 1 to 2 years. Today, some chips contain billions of transistors on something the size of a toenail. This is due to each transistor being the size of an HIV virus, which is very small. However, there has to be a limit, right? It has been accepted this law is close to reaching its physical limit of scalability due to power issues, including static power and dynamic power. In addition to physical limitations, there are also critical economic considerations affecting the future of CMOS technology. In order to overcome the dilemma, new forms of computation such as biocomputing, nanocomputing, spintronics, quantum computing, and optical photonic computing have been extensively researched on.
The biocomputing dataset is the largest in this project, with 2,160 publications between 2013 and 2016. The subset includes articles on biocomputing in terms of DNA and molecular computing, as well as brain-inspired computing such as neurocomputing and neuroformic computing. Biocomputing includes a broad range of computing approaches based on biological systems, ranging from the use of algorithms such as swarm intelligence, membrane computing, memetic computing, cellular automata, DNA, and molecular computing. Biocomputing has many diverse applications including computational intelligence, natural language processing, machine learning, algorithm theory, data mining, and many others. Capitalizing on the signal processing capabilities of biological systems, computing using biological entities can be implemented either on traditional electric hardware or on alternative physical media such as biomolecular computing such as DNA and RNA, or trapped ion quantum computing devices. However, while both electronic circuits and biological systems can process information, there are major differences in the wiring of the two. Electronic circuits have dedicated wires that prevent crosstalk, whereas biological networks respond to biochemical reactions that are subject to nonspecific chemical interactions, which in return can degrade the specificity of the signal, contaminate the memory, and eventually lead to a bad decision. Furthermore, a cohesive scientific understanding on how biological systems process information is still lacking for even simple cellular signaling, let alone for complicated neural circuits. An integrated understanding of how biological signals work, as well as the similarities and differences between man-made computing machines and biocomputing, is a central issue in the study of natural computing.
The Optical Photonic Computing dataset has 1,403 publications between 2013 and 2016. Optical computing uses light or photons rather than electricity or electrons to perform computational tasks. While optical photonic computing, or all optical computing, would ultimately be a complete replacement of electronic components with optical components, this has yet to occur, and most research has focused on the development of individual optical components to work in tandem with the electronic components. Photonic elements such as light sources, modulators, optical routers, photonic diodes/transistors, couplers, and logic gates can be regarded as optical analogies of electronic elements, but require careful design, construction, and materials to overcome the fundamental difference in principles and structures between electrons and photons. That being said, replacing on-chip electronic resources with optical components has a great potential due to the low latency and high bandwidth of light propagation. The more data transfer that occurs optically rather than electronically, the faster the computer can process information, particularly without various electrical loss, electrical noise, and crosstalk issues. All optical signal processing also has a high potential to overcome the bandwidth and speed limits of electronic circuits, with processing bandwidths up to several terahertz. Various optoelectronic integrated computing components exist on the market, including Intel's Thunderbolt, IBM's Signal Routing Chip, and Luxtera's and Infinera's optoelectronic integrated circuits, to name a few. Some recent accomplishments in the academic literature include the development of photonic circuits for wavelength division multiplexing, non-volatile photonic memory, and all optical logic gates, each of which now briefly described. When optical components are coupled with a WDM device, new opportunities emerge for parallel computation as multiple signals can be managed at the same time. However, the technology still lacks maturity. A new technology that consists of non-volatile photonic memory uses innovative phase-changing materials and eliminates the need to convert optical signals into electrical signals for data storage and then back again for data transmission, resulting in better efficiency and speed. Two subsets of photonic computing are nanophotonic and silicon photonic. The study of nanophotonics is young, but shows a lot of potential. The Spintronics dataset has 562 records between 2013 and 2016. Spintronics, sometimes referred to as magnetoelectronics, is an emerging technology that exploits both the spin instead of the charge and the magnetic moment of electrons 1, 2, 51, 57. When an electron is placed in the magnetic field, its spin polarization becomes bistable, which can be used to encode the logic bits 0 and 1. The idea of spin-based computing, in which Boolean logic gates are created through interacting electron spins, is the basis of spin-based quantum computing, which is known as magnetic quantum cellular automata. And therefore it ties back to nanomagnetic logic. Research on spintronics actually dates back to the 1970s, but saw renewed interest with the discovery of magnetic tunnel junctions and spin torque transfer devices. MTJ and STT devices provide potential avenues for replacing CMOS technology with spin-based integrated circuits such as magnetic random access memory and spin transistors. An MTJ is created when two conducting electrodes of ferromagnetic material are separated by a thin dielectric layer, insulator, or tunnel barrier layer through which electrons can tunnel, resulting in electrical conduction. Each of the ferromagnetic electrode layers act as either a storage layer or a reference layer. The electric current that tunnels between them consists of two partial currents, each with its either spin up or spin down.
Moving on, let's look at nanocomputing, which has the smallest dataset compared to all the other next-gen computations at 71 publications between 2013 and 2015. Nanocomputing describes computing that uses extremely small or nanoscale devices. It involves the use and manipulation of molecules and atoms themselves. The applications of nanotechnologies are unclear at this point. However, it's certain its roots lay in obscure and near science fictional thinking, such as nanometer-sized assemblers that can build other products and work together, self-replicating machines that would take in feedstock and produce self-replicas. In a brief overview, nanomagnetic logic, NML, is an extension of QCA in that it can be viewed as magnetic implementation of QCA, where information signals are processed through magnetic field interactions in nanocells. As such, it is also known as field-coupled computing, or previously known as magnetic QC, MQCA. While the electron-based version of QCA is susceptible to size variations, nanomagnets, which exhibit a collective spin behavior, are more immune to structure variations. The nanomagnetics used in NML have bistable magnetizations directions, up or down, and process signals via magnostatic field coupling. They are transistorless, can achieve non-volatility, high-density integration, and have ultra-low power consumption. To date, NML devices have proven to meet the 5 basic tenets that are considered essential for digital systems, including having nonlinear response characteristics due to magnetic loops, delivering a functionally complete logic set enabled by the 3-input majority gate, and the NOT operation naturally achieved by the anti-ferromagnetic dot-to-dot coupling, having signal amplification greater than 1, which is demonstrated by showing the feasibility of a 1:3 ratio fan-out, where the energy for the gain is provided by an external clocking field, being able to have the output of one device drive another, as the fringing fields from individual magnets can bias a neighbor, and finally, being able to prevent unwanted feedback through clocking. So what is quantum computing? Well, in order to understand what quantum computing is, first let's take a look at a classical computer. A classical computer performs operations using classical bits, which can be either a 0 or a 1. In contrast, a quantum computer uses quantum bits, or qubits, which can also be set to a 0 or a 1. However, the difference being they can be a 0 and a 1 at the same time. This is called a superposition. This is essentially what gives quantum computing its superior computing power. So what is a qubit? Well, qubits can be made from physical objects that can be used, such as a photon, a single nucleus, or even an electron. So let's look at how electron qubits work. All electrons have magnetic fields, which results in them having a spin. When you place them in a magnetic field, they will align in that field, and that is known as the lowest energy state, or spin down. They can also be put in a spin up state, which is the highest energy state, or spin up. If we make 3 spins, which would have 8 different states, and would give 8 different numbers, our classical computers would just give us 3 bits of information. This means the power combined in qubits is 2 to the n being classical bits. A qubit state is only determined the second it is measured. As long as it's unobserved, the qubit is in a superposition of probabilities of 0 and 1, and you can't predict what it will be. Although it can be any combination of any state, the moment they are measured, they must fall into one of the basis states, and all the other information about the other states is lost, as you cannot measure a superposition at all. This means Schrodinger's cat can be dead and alive at the same time. Qubit manipulation. A normal gate gets a simple set of instructions and produces one definite output. A quantum gate manipulates a superposition, rotates probabilities, and produces another superposition as an output. So a quantum computer sets up some qubits, applies quantum gates to tangle them, and manipulates probabilities, and finally measures the outcomes, collapsing superpositions into a sequence of zeros and ones. This means you can get the entire calculations that are possible in your setup all done at the same time. Ultimately, this also means you can only measure one of the results. However, by exploiting superpositions and entanglement, this can be exponentially more efficient than a normal computer. Unlike any other computers that are presently in use, a quantum computer provides a working condition where all the qubits are under the influence of each other. There is no observable interaction between the particles in the quantum environment. In a completely entangled state, a quantum computer with n qubits can entangle and superimpose 2 unclassical states into n qubits. Entanglement is essentially a close connection that makes each qubit react to a change in the other state instantly, no matter how far apart they are, even if they're on the other side of the universe. This means when you measure one qubit, you can directly figure out properties of its partner without even having to take a look. Parallelism. In reality, a classical operation that has 2 n inputs would require 2 n gates or have to wait for 2 n turns to produce a truth table as an output, whereas a quantum gate with 2 inputs would only take a single operation to produce a truth table as an output. Parallelism is a property that allows a quantum computer to perform multiple operations at one time without waiting for another process to complete, or there not being a need for more hardware to perform the same process. However, in these gates, processing an input and producing an output takes considerably longer time. So does this mean that we should forget about our current PCs? Well, not really, because things like watching Netflix or browsing the internet would be much faster on a classical computer, because quantum computers are only faster in special types of calculations where you have to know all the superpositions at the same time. They are superior only in certain areas, such as database searching. So why should we research it? Well, as Moore's law states, the number of transistors doubles every 18 months. However, this is expected to come to an end soon. This means that new means of advancements must be thought of, as classical computers have limits. First of all, we should understand that quantum algorithms can only solve the problems that a classical computer can solve, but it can solve a problem much faster than a classical computer in various instances, such as integer factorizations, search algorithms, etc. This exponential speed is because of the fact that a quantum computer can carry out certain computations faster than a classical computer. Most of the successful quantum algorithms use quantum Fourier transforms in them, and this is because of the fact that they require much lesser hardware. In quantum Fourier, it transforms the gates needed for computing n qubits, which is much lesser than a classical computer. That is the reason why Shor's algorithm for integer factorization is faster. It would only require lesser hardware, as it is based on quantum Fourier transforms to carry out the repeated operation that the algorithm uses. Another such algorithm is Grover's search algorithm. Here, faster search is possible as there are multiple processes running in the system at the same time, computed using quantum Fourier transforms. Some of the breakthroughs in quantum computing is that Today there are quantum computing labs with working models of quantum computers to test these algorithms. The D-Wave is a quantum computing company that has come out with the actual working model of quantum computers. The 512-qubit chip system, called the D-Wave 2, is to be installed in a NASA installation to allow researchers to work on some tough computer science problems involving machine learning, speech recognition, web search, search for exoplanets, planning and execution in mission control centers. No one knows how it would turn out to be in the coming years, but one thing is for sure, is that quantum computers are going to change the face of computing by allowing us to overcome some of the limitations that a classical computer faces. Some of the potential of quantum computing is machine learning, supply chain optimization, robotic manufacturing, computational materials.
Today's technology and chips all use copper wiring to transmit their signals. They are in the smartest computers to the basic calculator. Almost all modern devices rely on copper wiring. It is cheap and reliable, but it does have its drawbacks. As we come to the limit of Moore's law, the shortcomings of copper wiring come into focus. Issues such as limited bandwidth, current leakage, and wire crosstalk limit the industry to only being able to innovate to a certain point. Even practical concerns such as the space copper wire takes and the power consumption and the heat they emit. Enter optical photonics. One solution to the issue that copper wiring chips contain is light-based technology. An example of light-based technology is what some companies, such as Verizon, use to get the customers into buying their product. Fiber optics or optical fiber cables are an example of such technology. They use the photons of light to send and transmit data, which leads to faster speed and more bandwidth. But this does come at a cost. The issue that this leads to is the same issue the customer would bring up, the cost. The cost for replacing electric wiring in integrated circuits with cutting-edge photonics has proved to be a roadblock to commercialization. What is needed is a photonic technology that can be made using existing, high-volume, inexpensive manufacturing methods. Solution. The cost issues of light-based technology can be remedied by silicon photonics. Recently, silicon photonics has seen a significant increase in research. Silicon is a major candidate material for implementing integrated photonics. Silicon supports the ability to create compact nanowires for guiding light on chips and facilitating integration with silicon-based technologies. Its great advantage is that it can be manufactured just like normal computer chips, but with patterned silicon to transmit data carrying laser signals. Silicon photonics. In general, combining silicon with integrated photonic devices takes advantage of the ability of large wafers, ease of handling, and thermal cycling, high volume throughput, and cost reduction of silicon manufacturing for photonic devices. Furthermore, it offers orders of magnitude improvement in bandwidth, latency, reliability, and power efficiency. Advantages: more compact optical waveguides, lower optical propagation loss, better processing yield, low cost, greater compatibility with CMOS electronics. Caveats: although silicon photonics is a perfect solution on paper, scientists have struggled to find the solution of silicon. Silicon is opaque on the visible spectrum and it is transparent under infrared wavelengths, which allow the ability to guide light properly, but the problem lies in emitting light from silicon. Silicon photonics expert Lars Frentzen from Technical University of Denmark gets into the technical details. The electronic band gap of silicon makes it transparent in the telecommunication wavelength range, but it is an indirect band gap, which makes silicon a very poor emitter. This is why the lasers that drive optical communications are made from more exotic materials such as indium phosphide and gallium arsenide. Combining other technologies, materials, and wavelength platforms with silicon photonics seems to be the path toward photonic integrated chips. These chips that make multiple technologies will most likely dominate the integrated optoelectronics in the coming future. These heterogeneous silicon photonic integrated circuits have several advantages, including reduced cost due to economy of scale, better performing devices than those using only III-V materials, low power, high capacity, volume, yield, and reliability, introduction of non-linearities and magnetic properties, suitability for reliable active photonic devices such as lasers, modulators, and photodetectors. Today's uses. The challenge of designing integrated silicon photonic device is actively being pursued by both industry and academia. CMOS-compatible photonic devices such as the micro-ring resonators, photodetectors, waveguides, network-on-chip architects, and 3D architects are being researched. Despite silicon shortcomings, some silicon photonic devices are being made. Companies such as Luxtera shipped a silicon integrated chip in 2008, and has shipped more than 1 million of them. Tech giant Intel brought its silicon technology in 2016, while IBM and Cisco follow close behind. In 2015, U.S. researchers described in a Nature paper how they demonstrated the first photonic-electronic hybrid processor that uses light for ultra-fast communication, packaging two processor cores with more than 70 million transistors and 850 photonic components onto a 3x6 mm chip. It was the first to integrate photonic interconnects or inputs and outputs required to talk to other chips. Staggeringly, the chips had a bandwidth density of 300 gigabits per second on millimeter square, and a 10 to 50-fold improvement on electronic-only microprocessors. The achievement did, however, come with a caveat. The team had to use externally generated laser lights to illuminate the chip. Conclusion. Despite these challenges, it seems that researchers are accepting the drawbacks of hybridization and that heterogeneous silicon photonics is the best known approach for the foreseeable future. Furthermore, photonics continues to have the potential to play a significant role in future computing by allowing high bandwidth and low latency transfers between the processing chips and the main memory, thereby helping to alleviate main memory bottlenecks. Moore's law might be approaching its limit, but it doesn't mean that innovation has to stop.